Since the overall purpose of this segment of course is to prepare the way for petrogenetic studies of igneous rock. Certain fundamental concepts should be borne in mind during examining the rocks. The two very important things to consider are the Bowen reaction series and igneous rock classification. In this program, we will focus on the Bowen reaction series. Within the field of geology, Bowen's reaction series is the work of the petrologist Norman Bowen, who was able to explain why certain types of minerals tend to be found together while others are almost never associated with one another. The early experimental work of Norman Bowen revealed that as magma crystallized out with falling temperature, each mineral was restricted to a certain definite temperature interval. Although the actual temperature of crystallization can be modified by varying the pressure, the order of crystallization of minerals remain the same. He experimented in early 90s with powdered rocks material that was heated until it melted and then allowed to cool to a target temperature. Whereupon, he observed the types of minerals that formed in the rocks produced. He repeated this process with progressively cooler temperatures, and the results he obtained led him to formulate his reaction series, which is still accepted today as the idealized progression of minerals produced by cooling magma.
The Bowen reaction series is still having a very important significance within igneous petrology, because on the basis of Bowen reaction series, we can study how the different minerals are formed at different depth and different temperatures. They may be a silica undersaturated or silica oversaturated mineral.
The Bowen reaction series having two branches, the continuous and the discontinuous. The branch on the right is the continuous. The mineral at the top of the illustration are first to crystallize, and so the temperature gradient can be read to be from high to low, with the high temperature minerals being on the top and the low temperature ones on the bottom. Since the surface of the earth is a low temperature environment compared to the zones of rock formation, the chart also easily shows the stability of minerals, with the ones at bottom being most stable and the ones at top being quickest to weather. This is because minerals are most stable in the conditions closest to those under which they had formed. Put simply, the high temperature minerals, the first ones to crystallize in a mass of magma, are most unstable at the earth's surface and quickest to weather because the surface is most different from the conditions under which they were created, while the low temperature minerals are much more stable because the conditions at the surface are much more similar to the condition under which they formed. The mafic, that is magnesium iron minerals, interact with the remaining magma and give rise to mafic mineral of different structure as the temperature falls. These define the discontinuous reaction series. If suppose we move from top to bottom, that is right olivine to biotite, there is a decrease in temperature and structure evolved from mesosilicate to phyllosilicate. The felsic minerals also start crystallizing out at high temperature and interact with magma with falling temperature. However, the main group retains the basic changes in composition by solid solution. Thus, defining the continuous reaction series, just for information, this is not an abstract concept. It means that if rock contains olivine, clinopyroxene and biotite, then that is also the sequence of formation for these minerals. Bowen's reaction series is usually diagrammed as Y with horizontal lines drawn across the Y. The first horizontal line, usually placed just above the top of the Y, represents a temperature of 1800 degrees Celsius. The next horizontal line represents a temperature of 1100 degrees Celsius and is located 1/3 of the way between the top of the Y and the point where the two arms join the base. A third line representing a temperature of 900 degrees Celsius is located 2/3 of the way from the top of the Y to juncture of the upper arms. A fourth horizontal line representing a temperature of 600 degrees Celsius intersect the triple point junction where the upper arms of the Y meet the base portion. The horizontal temperature lines divide the Y into 4 compositional sections. Mineral formation is not possible above 1800 degrees Celsius. Between 1100 degrees Celsius and 1800 degrees Celsius, rocks are ultramafic in composition. Between 900 degrees Celsius and 1100 degrees Celsius, rocks are mafic in composition. Between 600 and 900, rocks are intermediate in composition. And below 600 degree, felsic rocks form. Now we discuss in detail the discontinuous reaction series. The left hand side of Bowen's reaction series, these are a group of mafic or iron magnesium bearing minerals: olivine, pyroxene, amphibole and biotite. If the chemistry of the melt is correct, these minerals react discontinuously to form the next mineral in the series. What this means in igneous magmas is that if there is enough silica in the melt, each mineral will change to the next mineral lower in the series as the temperature drops. As you go down Bowen's reaction series, the mineral increases in the proportions of silica in their composition. In a basaltic melt, olivine will be the first mafic mineral to form. When the temperature is low enough to form pyroxene, all of the olivine will react with the melt to form pyroxene, and pyroxene will crystallize out of the melt. At the crystallization temperature of amphibole, all the pyroxene will react with the melt to form amphibole, and amphibole will crystallize. At the crystallization temperature of biotite, all of the amphibole will react to form biotite, and biotite will crystallize. Thus, all rock should only have biotite. But we know that it is not true. If you are crystallizing olivine and there is not enough silica to form pyroxene, then the reaction will not occur and olivine will remain. If you are crystallizing olivine and the temperature drops too fast for the reaction to take place, then the reaction will not have time to occur. The rock will solidify quickly and the mineral will remain olivine.
If suppose we will see the discontinuous series where the olivine, pyroxenes, amphiboles and biotite are there. The olivine crystallize in nesosilicates, or in other words we can say the silicon oxygen ratio is 1:4. Similarly, the next minerals with slightly above the olivine crystallize, that is your pyroxenes, and pyroxene crystallize in inosilicates, where the silicon oxygen ratio is 1:3, and after that amphiboles, which crystallize in again in inosilicates double chain, and the silicon oxygen ratio is 4:11, and after that biotite, which crystallize at slightly above of all these minerals, where the silicon oxygen ratio is 2:5. If suppose we'll see the evolution point of view, the olivine is a primitive in its structures as compared to biotite, more which are having seed silicate structures, and silicon oxygen ratio is 2:5. The right form, if suppose we move from olivine to biotite, there is a structure is evolved. Depth wise, if suppose we will see, then depth is reduced right from olivine to biotite. Similarly, the temperature also reduced from olivine to biotite.
As we see in the diagram, the right hand side of Bowen's reaction series, they are all the plagioclase. Plagioclase minerals have the formula CaNaAl3Si3O8. The highest temperature plagioclase has only calcium. The lowest temperature plagioclase has only sodium. In between, these ions mix in a continuous series from 100% calcium and 0% sodium at the highest temperature to 50% calcium and 50% sodium at the middle temperature to 0% calcium and 100% sodium at the lowest temperature. For example, in a basaltic melt, the first plagioclase to form might be 100% calcium and 0% sodium plagioclase. As the temperature drops, the crystal would react with the melt to form 99% calcium and 1% sodium plagioclase. And 99% calcium and 1% sodium plagioclase would crystallize. Then those would react to form 98% calcium and 2% sodium, and the same composition would crystallize. All of this is happening continuously provided there is enough time for the reactions to take place and enough sodium, aluminium and silica in the melt to form each new mineral. The end result will be a rock with plagioclase with the same ratio of calcium to sodium as the starting magma. On both sides of reaction series, as we see in the diagram, the silica content of the minerals increases as the crystallization trends heads downward. Biotite has more silica than olivine. Sodium plagioclase has more silica than calcium plagioclase.
The calcic sodic plagioclase, and another bottom point is your sodic calcic plagioclase. Basically, the pure calcic plagioclase is your anorthite, and pure sodic plagioclase is your albite, and they have a solid solution series with a combination of different calcium-sodium ratio and give rise to oligoclase, andesine, labradorite, bituminite, and members. Anorthite crystallizes at higher temperature, nearly 1553, as compared to albite, which is crystallized at 1108 degrees centigrade.
The time that the magma is allowed to cool will then determine whether the rock will pegmatite, pheneritic, aphanitic, or glassy in texture. When magmas experiences differential cooling, they produce porphyritic rock, a mixture of crystal, and exhibit either a pheneritic or aphanitic ground mass. Bowen's reaction series allows the prediction of mineral content in rock by examination of rock, allows the reverse determination of the condition under which the magma cooled and igneous rock formed. Examples of the use of Bowen's reaction series are given in figure. From the top diagram, you can interpret the physical and chemical conditions under which a mineral crystallized. For example, olivine is a high temperature and pressure mineral with high iron and magnesium and low silica. Secondly, the bottom diagram shows mineral association and exclusion in a rock. The minerals in each rock are horizontal across the diagram. Basalt would have olivine, pyroxene, and high calcium plagioclase, but would not have quartz and potassium feldspar. The top diagram shows mineral stabilities in a weathering environment, the least stable at 1 bar and 25 degrees Celsius. The least stable minerals are at the top of the diagram and the most stable at the bottom. A basalt contains olivine and calcium plagioclase. If it is being weathered, these minerals are very unstable and will readily break down by dissolving and forming clays. A granite contains quartz, potassium feldspar, and muscovite. The muscovite and potassium will readily break down, but the quartz is fairly resistant. When the products of the weathering of basalt and granite are eroded and deposited, you would expect to find lots of quartz, maybe some potassium feldspar and muscovite, and no olivine and calcium plagioclase. Fourthly, the rocks at the top and bottom of Bowen's reaction series should not occur in same outcrop. The conditions that produce basalts are not the same as those that produce rhyolite. If a basalt has quartz in it, which occasionally occurs, the quartz must have come not from the magma, but from the rock into which the basalt was intruded.